Thank you so much for having me here. And my name is Robert. Today, I'm going to tell you about recent advances in predicting properties of quantum many-body systems. So I will begin with our original work published last year at Nature Physics, and then I will dive in to some more recent works that try to extend upon us and study related questions. So the main motivation for our original work is to understand how we can construct accurate classical representation of a many-body quantum system efficiently. So suppose you have this unknown quantum system that you prepare in your lab or your quantum computer. You wanted to construct this efficient classical representation such that you can use this classical representation to predict various properties of the original quantum system. So why do we care about this task? So first, from an experimental point of view, when we design a quantum device such that you can prepare certain interesting states like a torical state or GHE state or various different states, you wanted to know if you have constructed it accurately. And then that means you wanted to have some understanding of what this quantum system that you constructed is and use it to calibrate your device or to improve upon it, etc. And another important motivation is basically this variational quantum algorithm that I've been talking about in the tutorial. So a lot of these quantum applications actually require this type of hybrid classical quantum algorithms where you have quantum computer preparing states and then using classical computer to try to optimize your quantum computer, such as minimizing Hamiltonian or minimizing some really want to have this kind of interface between quantum computer and your classical computer such that, and a very efficient interface such that you can do the optimization or do these kind of hybrid algorithms much more efficiently. So what are some key aspects for this type of task? There are essentially four of them. First is sample complexity. So in quantum system, you have this wave function collapse problem. So basically like when you measure the same system and under the same measurement result, you will get different outcomes. And every time you get an outcome, your original quantum system would be destroyed. So you actually need multiple copy of your quantum system. And that's characterized by the sample complexity. That is how many copy of your quantum system is required to get this classical representation. There's also quantum resource, which is how expensive it is to measure the quantum system. You can have like very deep quantum circuit for measuring the quantum system or like a very shallow circuit. That's the quantum resource. You would also have classical storage, like how big is your classical representation, as well as classical post-processing, like how efficient it is to represent and to predict properties and so on. So the standard approach for this task is known as quantum state tomography, where the idea is to learn a full, complete representation of your quantum system. So here, this complete representation would be your density matrix, which is a d by d matrix, and d is equal to 2 to the n, where n is the number of qubits in your system. So this complete representation is an exponentially large matrix. So even the optimal protocol, due to Zhao and Ha et al., Ryan O'Donnell and John Wright, even for the optimal protocol, all the aspects scales exponentially. So you need an exponential number of copies. You also need this exponentially deep circuit. And then after that, the storage is exponential and any post-processing, like computation time, is also exponential. So this would always occur if you wanted to learn the full representation of any quantum system. And in order to circumvent this exponential scaling, which is clearly not scalable to like 50 qubits or 100 qubits or more, there have been a lot of recent developments. One of it is called shadow tomography, where the key idea is you don't learn the full representation of your quantum system, but you just directly predict a large number of properties. So in the original scheme of shadow tomography, they consider expectation values of observable. So that will be given by this trace OK rho for different observable from O1 to OM. So in this case, this task is actually much simpler than learning the full description. And the best rigorous protocol, due to Badescu and Ryan O'Donnell, uses a sample complexity, number of copies of your system, that's very efficient. So previously, for learning the full representation, the sample complexity scales exponentially in system size. But now, as you can see, the number of copies you need only scales linearly in system size. And then the scaling with the number of properties you wanted to predict is also very efficient, only logarithmic, like log m squared. However, for this best rigorous protocol for shadow tomography, the quantum resource requirement is also very expensive, and the storage as well as post-processing time are also still exponential. And it's actually not classical exponential, but quantum exponential. So like you need quantum circuits that's exponentially deep and so on. So it's still very expensive, but the sample complexity at these is very efficient. So that gives us some hope to improve upon it. Another very, very different line of research is based on machine learning, where the idea is to perform some simple quantum measurements, and then you just train a neural network to represent the quantum state. So you just do the simple quantum measurements, say you perform some single qubit rotation, like in this POVM neural network tomography, you just perform some single qubit rotation, do a basis measurement to gather your data, and then you just train a neural network to represent the quantum state based on the data that you obtain. So while the quantum resource part of it is very efficient, it's unknown what all the other aspects are, because due to some of these black box aspects of neural networks, people don't really know what are the number of copies required to represent the quantum state. They also don't really know what the true classical storage and the post-processing times due to the unknown aspect for the sample complexity. So in Nature Physics paper, the main question that we wanted to solve is to understand if we can find a provably efficient procedure that does the following. So first, in step 1 for data acquisition, it learns some classical representation of an unknown quantum state from few measurements. So you can think of this classical representation as a rigorous version of the neural network procedure. And then furthermore, at the second step, you can just use the classical representation to predict many properties of the quantum state rho with rigorous guarantee. So unlike in neural network, the prediction could be crazily off. We want the procedure that is always correct. So in order to answer this question, in our paper, we proved the following theorem. We showed that there exists a procedure that given two constant b epsilon greater than 0, the procedure would learn a classical representation of any unknown quantum state rho from only b log m over epsilon squared measurements. And subsequently, given any observables, O1 to Om, with a bounded norm bounded by this constant b, the procedure can use the classical representation to predict the expectation value of all these m observables, trace OI rho, up to epsilon error. So for example, if you wanted to measure 10 to the 6 different observables with the norm bounded by 1, then naively we would require 10 to the 6 over epsilon squared measurements. So basically you just look at each observable and then you measure them sequentially. So that would require 10 to the 6 over epsilon squared measurements. However, this theorem shows that we actually only need 6 log 10 over epsilon squared measurements, which is a significant reduction from 10 to the 6 over epsilon squared measurements. Furthermore, we actually don't need to know these observables O1 to Om in advance. So in order to understand how the theorem works, let's look at what the procedure that we constructed such that looks like, such that we guarantee the statement shown here. It's actually a very simple procedure based on randomized measurement. So first, let's look at the data acquisition phase. So you have some quantum system shown here that you construct in a lab. You wanted to gather some data such that you can construct this classical representation. Basically, we just do the following. So we first sample a random unitary, UI, to rotate your quantum system, so like to slightly involve it. And then we just measure the system in a computational basis to obtain this bitstream BI. So in order to understand this protocol intuitively, let's consider this quantum system as a very high dimensional object. Here in this bottom right figure, we just represent the quantum system using this like three-dimensional object. Every time when we do this randomized measurements, what we're doing is we're essentially looking at this quantum object from some angle, like basically you rotate it, and then you just measure in the classical basis. So that's equivalent to looking at it from some angle and then projecting it onto the classical space to get this classical bit stream BI. And then you just repeat. So for example, when you look at it from this angle, you see like a square. You look at it from a different angle, you see like a circle, and then you see like this triangle. After seeing all these like, as shown in the figure, like all these shadow of the original quantum system, we can get a good picture of what the original quantum state or this very high dimensional object looks like. And that's sort of the basic idea for our randomized procedure. So every time we do this randomized measurement, we sample this UI, get this BI, and then we just store this classical shadow, which is denoted by this quantum state SI equal to UI dagger BI. So that's basically just when you rotate your system, get the classical sort of snapshot, you just rotate it back using UI dagger. So in practice, we don't really store this classical shadow as a quantum state on your classical device, but all you store is this classical bitstream BI as well as a classical description for your random unitary UI. So it's all very efficient. And now let's look at this protocol from a very simple single rabbit illustration. So it's basically just a real qubit. So let's suppose that your quantum state is this row, this green point row. And suppose you first measure in this plus minus basis. When you measure in this basis, it's more likely that you will get the plus state. So for the first round, let's say you really get the plus state, then your S1 would be equal to plus. And now suppose in the second round, you measure in the 0, 1 basis, then S2 would be equal to 0. And it's more likely that you would get 0. So let's say S2 is equal to 0. Then when you average over them, this row hat 2 would be this point. And suppose you just keep on doing this for an infinite number of times, it will actually converge to a point, rho hat infinity, that's also equal to the expectation value of your classical shadow for a single round of randomized measurements. And furthermore, you can actually analyze this and prove that this rho hat infinity, or the expectation value of S, is equal to applying a depolarizing channel onto your original quantum state row. So together, what you get is, and actually more generally, for any distribution over the random unitary, you can always write down the expectation value of this classical shadow SI to be equal to some CPTV map M applied onto the original quantum state row. So you can actually prove this for any distribution over random unitary. So given this equality, we can start looking at the prediction step. So suppose that you have done n rounds of randomized measurements to get this classical like classical snapshot S1 to Sn, also known as, we also call it as the classical shadow. How do we predict properties of the original quantum state row? And we will utilize this equality. And basically what we do is we just invert it. So we just have this linear inversion estimator of rho being equal to expectation value of M inverse applied on SI. Which means that if you just do one single shot measurement, this matrix would actually be close to our original quantum state row. Which means that we can just use this to predict properties of the original quantum state. So an algorithm for estimating trace row is given as follows based on this median of means estimator. We basically just replace rho by the single shot classical shadow, and to get an estimate. So xi is a real value that would be equal to trace O rho and expectation. What we do is we chunk this all these data up, take the average for each chunk, and then take the median of the entire thing. So this median is quite important for a certain distribution of random unitary in order to like boost the statistical deviation, boost this convergence such that this O hat would be very close to trace O rho with much higher probability. And just by using this very simple procedure and doing proper statistical analysis, you can prove this theorem showing that you actually only need b log m over epsilon squared measurements to estimate the expectation value for m observable, which is quite a surprising fact a year ago. And based on the theorem, you can actually show a lot of wide range of results by tuning the distribution of the random unitary. For example, you can use it to efficiently predict fidelity or entanglement weakness, entanglement entropy, or topological entanglement entropy, two-point correlation function, Hamiltonian, or local observable. So a lot of wide range of different properties that you care about in practice can all be efficiently characterized using this classical shadow framework. So while we only talked about the theoretical part, let's look at some numerical experiments that we did in our original work. So this experiment considers predicting quantum fidelities. So we assume that in the lab, we have prepared some GSG state, possibly with some noise on top of it. And then what we wanted to do is we wanted to get the classical representation of the GSG state and use the classical representation to estimate the fidelity, like whether we have prepared the correct GSG state or actually we've prepared something wrong. And we compare it with this neural network quantum state tomography, which is this blue dot. Consider different system size and the number of experiments in order to achieve 0.99 fidelity on the GSG state. You can see that the neural network quantum state tomography is performing really well, only scaling linearly in system size rather than exponentially in system size. However, you can see that classical shadow only requires a number of experiments that scales constant. So as you can see in this procedure, in this theorem that we show, there's no dependence on the system size of your quantum system rho. It only depends on how many properties you wanted to predict, this log n. So that was the, yeah, so that's why it shouldn't depend on system size at all. And yeah, so it also improves upon this neural network quantum state tomography. And in figure B, we consider when there are some noise in your GSG state, and you're estimating the fidelity of the noisy GSG state against a pure GSG state. So as the probability of error increases, your fidelity should go down, and that's denoted by this dashed line. And as you can see, classical shadow prediction accurately tracks it. However, we found that since neural network quantum state tomography doesn't really have like provable guarantee and so on, it can actually sometimes provide erroneous prediction. So this is what's happening. Like the neural network quantum state tomography is overestimating the fidelity because it couldn't really estimate the true fidelity very efficiently. So it's only estimating an upper bound, like this classical fidelity of the quantum fidelity, which would cause this problem that you're not getting the true fidelity accurately. You're not tracking the true fidelity accurately. So that's the first demonstration. There's also a lot of others. For example, this predicting entanglement entropy experiments. Here we're looking at, in figure A, we're looking at the approximate ground state of disorder Heisenberg model, which would be given by this random singlet face. So basically you just have a bunch of Bell pairs as your ground state. And here we're just plotting the entanglement entropy for all subsystem of size less than or equal to 2. And using classical shadow, you get this plot for the estimated entanglement entropy, which is much more cleaner than this specialized approach due to Bridges et al., published at Science at 2019. A similar situation holds for predicting entanglement entropy in GSG state, you see that for different number of experiments, using classical shadow give you a boost in the prediction performance. That is, you get quite a bit lower prediction error compared to this specialized approach. And finally, we also consider this other application for simulating one-dimensional quantum electrodynamics. So this is a variational quantum simulation of lattice Schringer model falling into this regime or this setting by the tutorial session. So in this kind of, in this application, we consider some quantum simulator parameterized by some parameters, theta 1, like all these thetas, such that every time what you do is you try to prepare a trial state for your fermionic field. And after preparing this fermionic field, you use classical shadow. Basically, you just apply a random unitary, do measurements, repeat for a few times to get the classical representation. And after that, you use this classical representation to predict all the observables involved in estimating the Hamiltonian variance. So when you expand this Hamiltonian variance, you'll see that it's basically a sum of 4 body observables, a very large number of them. And you just use classical shadow representation to predict all of them using only logarithmic amount of measurements. So after getting the Hamiltonian variance, you feed it into a stochastic optimizer, which will tune this variational parameter theta to minimize the Hamiltonian variance. So it's known that if you're preparing a pure state and your Hamiltonian variance is equal to 0, you're at an eigenstate. So by doing these iterations, by minimizing this Hamiltonian variance, where you use classical shadow to predict Hamiltonian variance, you can minimize this. Yeah, you can find the eigenstate for the lattice Schringer model. So here in figure B, we compare our approach with a large number of reason and specialized approaches. Like this blue line was done by physicists in Austria, where they just look at this Hamiltonian variance and try to be creative and figure out sort of what is the best measurement scheme to measure all these observables, all these 4-body observables in Hamiltonian variance. And they were able to reduce the number of measurements from originally, I think it's n cubed or n to the 4th into only linear. So this blue line is linear in system size. As you can see, if you use classical shadow, it's like the red line or the orange lines. You will be able to get something that scales only logarithmic with system size. So even improving upon this handcrafted approach. And there are also other approaches, like if you just do direct measurements, or if you do this partial tomography by Google, you can see that using classical shadow has a lot of benefits over these existing approaches. So that's pretty much it for our original work. And for the rest of the 15 minutes, I wanted to talk a bit about some of the recent developments along what we have done previously. So while classical shadow have good like theoretical guarantee and numerical demonstration, there are still various aspects that remains unclear, and these recent developments actually try to clear up and to improve upon our original proposal. So first, of course, is experimental demonstration. So previously, we only did like numerical simulation of classical shadow. And we are actually really curious before that how would it fare, like how would it behave in an actual physical experiments. So in this reference one, published at PRX Quantum, it was a group of scientists from Russia where they implemented this classical shadow protocol in a quantum optical experiments with high-dimensional spatial states of photons. And they found that classical shadow actually works really nice in an actual physical setup. So these blue dots are the prediction using classical shadow. And they found that for large number of experiments, like if you do 10 to the 4 number of experiments, then classical shadow and this more traditional approach, maximum likelihood estimate, actually have similar performance. However, when you go to the low measurement regime where you only do like 100 or 300 number of measurements, then classical shadow actually provides a better prediction compared to MLE. So MLE actually provide a erroneous prediction for the properties that you wanted to predict, while classical shadow can accurately provide an accurate estimate, but with some variance in the prediction. And furthermore, in this reference to published at PRL, we are Richard Kuhn, me, and John Presco, along with Peter Zoller's group, we extended classical shadow for verifying entanglement in actual physical system, and we actually ran it on their device and showed that using this, you can accurately track the entanglement. Like you can actually accurately track entanglement in this mixed state systems. So sort of clearing that it's not just a theoretical thing, but it's actually very useful also in physical experiments and so on. However, in all these previous experimental demonstration, we're using measurement devices that's very clean and can get a lot of signals. There's not too much error or noise in your measurement device. But when there are actually measurement noise, so for example, the unitary that you applied is not really a unitary that's being done in the as what you think, or the measurement are erroneous, like you can have some local phase error or local bit fill error, then in those kind of cases, if you just use the original formula, then classical shadow will actually not approximate the quantum state unbiasedly, which means that if you use classical shadow in these kind of regime, you would actually get slightly off prediction. So if your noise is small, then the deviation will also be small. So you see like in their optical experiments, the prediction is very accurate. But when you go to a larger system size, you're going to have noise everywhere. And in that case, using classical shadow might not be very beneficial. So one way is how do you mitigate noise while retaining all these nice property of classical shadow. In these two very recent paper, one from Dex and one from Senrei, they study this, like they study approaches for mitigating noises and doing error mitigation in this classical shadow framework and found very decent improvements. So in the sphere to the right, it's from this robust shadow estimation from Senrei Chen and Steve. And here, they're considering like estimating fidelity for GSG state or estimating expectation value of Hamiltonian. So they consider different type of noise in your measurement device. The first one is you have like local phase error. The second one is like you have local bit flip error. So as the system size increases, this circle like this with a square are our original classical shadow approach. You see that the fidelity actually goes down quite a bit as your system size start to increase, or the error for predicting Hamiltonian also start to increase. But when you apply their technique using this robust shadow estimation, you can actually get a fidelity that's correct across the entire range of system size. And also when you use it to estimate expectation value of Hamiltonian, you can also see that you get like basically a zero prediction error, while if you use our original classical shadow, your prediction will be slightly off, increasingly off when the noise in your system start to increase or when your system size start to increase. So this is a fascinating work for improving the practicality of our original framework. And another important aspect is quantum chemistry, right? Like in the VQE session, we talked a lot about this quantum chemistry expectations. However, a key problem there is usually in quantum chemistry, all these molecular Hamiltonians that we wanted to measure are very high weight. That is, they act on multiple qubits in your system. And using our original theory, classical shadow cannot efficiently predict high weight Pauli observables due to this large shadow norm that's defined in our theorem. So it's very crucial and important to understand how we can improve upon this. So in this two paper, this 5 from Charles Hadfield from IBM, and our follow-up paper, this efficient estimation of Pauli observable by de-randomization, we consider two different extensions, like very different extensions to our original classical shadow, mainly focus on applications in quantum chemistry. So the key idea in this paper 5 is that they wanted to learn the distribution of the random unitary. So in our original proposal, we just fixed the distribution for random unitary. For example, you just randomly, like for each qubit, you just randomly rotate the qubit by a uniform random unitary. And then you do the basis measurements. But in this paper, they consider a sort of a learning approach where you will optimize the distribution of random unitary such that you minimizes the number of measurement required for a specific Hamiltonian you wanted to measure. So by tuning, like fine-tuning the distribution according to the Hamiltonian, you can actually get pretty big speed up. So that was, this table was from their paper. The classical shadow is our original approach. This LBCS is locally biased classical shadow. That is their proposed approach. You see that like by just biasing this distribution, you can actually utilize structures in the original molecular Hamiltonian, and you can get a speed up like 30 times of reduction in the number of measurements that's required, which is very decent. And another line for applying to quantum chemistry is from us, where we consider a very different approach. It's called de-randomization. So recall that in our original approach, every time we do this measurements, we are doing a randomized approach. We are sampling a random unitary, and then we are doing the measurement. So the key idea here is that we try to learn a full set of measurement procedure for a given Hamiltonian by de-randomizing the randomized measurements. So what is de-randomization? It's a theoretical computer science concept where every time you wanted to apply this randomness, like you wanted to select a random unitary, you replace that by a fixed sort of a deterministic random unitary based on the best knowledgeable choice. So for example, if you wanted to measure each qubit in a random Pauli X, Y, or Z basis, you choose the one that minimizes some cost function. So that's basically what we do here. So like, suppose we do m rounds of Pauli measurements on all the qubits, then every time we just select X, Y, or Z according to some cost function, and you try to minimize that cost function. And then you just do it iteratively to fill in the entire measurement scheme. So m rounds of different experiments, you just fill that in using this automated procedure. And by choosing a proper cost function, you can actually, after doing the de-randomization, the final procedure that you come up with would always perform equally or better than the original randomized measurement. And in a lot of cases, especially in quantum chemistry application, it's significantly better than the original randomized measurements. So here is just a plot for measuring the molecular Hamiltonian for BH2 under Ravi-Kitav encoding. The yellow lines are the original classical shadow, and the blue line is when you de-randomize it. The y-axis is the estimated error, while the x-axis is the number of experiments. So you can see that this is like many order of magnitudes better than the original classical shadow for this like small molecule. And we expect that when you go to larger molecules, the improvement will be more and more significant using this de-randomization procedure. We also compare with locally biased shadow, which indeed improves upon classical shadow, but for the molecules that we tried, it seems like the de-randomized procedure actually improves even further upon this locally biased shadow. And we also compare it with this standard approach called largest LDF grouping. Basically, you just try to group all these Pauli observables into qubit-wise commuting groups, like a smallest number of possible, which is a very strong approach that's used in practice. But we found that using this de-randomization approach, you can even improve upon that as well. And also another interesting work to note is a work from Andrew Zhao and people at Google, where they consider extension of this classical shadow framework by replacing, so in our paper, we usually focus on random Clifford unitary because Clifford circuits are classically easy to simulate, so you can operate with it very efficiently. But they replaced it by this random fermionic Gaussian unitary, which is also classically simulable. And then it's much more suited for fermionic systems. And then they also observe some pretty substantial improvement over existing methods like sorted insertion, fermionic swap network, which people have originally believed that those are pretty much the best. But when you apply this random fermionic Gaussian unitary, it seems like you can get a further improvement on top of it. And finally, just wanted to point out another very different line of thoughts. As extension is predicting outcomes of physical experiments. So originally in this classical shadow work, we consider predicting properties of quantum states based on this randomized measurements. But it would be natural to expect like what would happen if we extended to predict outcomes or predict properties of CPTP maps. So a practical usage would be predicting outcomes of physical experiments. Like in chemical experiments, you have all these molecules that's being involved. Could you predict the outcome of what would happen in the experiments, in the chemical experiments, without actually doing the experiments? So could you train some kind of a model, like an ML model, for this kind of setting? So what we show in this paper 8, we consider a learning procedure that also just performs some randomized physical experiments to gather this classical data. And then we have this learning procedure that would use the classical data to predict outcomes of a new physical experiments. And furthermore, we showed that the prediction performance is actually similar to the optimal quantum machine learning procedure that can gather and process quantum data. So to conclude, classical shadow provides a rigorous and practically efficient procedure that allows classical machines to sort of like see quantum systems, quantum antibody systems. And this rigorous procedure also provides a lot of empirical advantages over existing approach. I wanted to note that while various progress has been made, many open questions still remain to be answered. For example, can you get better sample complexity for physically relevant systems? And whether you can simulate quantum dynamics with classical shadow, or if you can solve quantum many-body problems with a combination of classical ML and classical shadow. So that's it for my talk, and thank you so much for listening.